Everyone, welcome back to the channel. I'm Tanya Chiu, your online physics tutor. In this video, I am going to tackle the latest IGCSE Physics past year paper. That is February-March 2025, paper 42 from extended syllabus. So if you're preparing for your upcoming exams, okay, maybe May-June 2025 exams or October-November 2025 exams or any other upcoming exams, this is exactly what you need because I am going to walk through each question with you, talk about how to break down the tricky part, and I will also share you some useful tips to avoid the common mistakes students make. So are you ready to dive into answering the question? Let us do this together. Now this is the paper. This is Cambridge IGCSE Physics, paper 4, theory part, extended syllabus. And this is February-March 2025 with code 0625/42. Let us look at the first question. Fig 1.1 shows a force extension graph for a spring. So when you look at the graph, oh, this is a force against extension graph, right? And it is a straight line graph indicating that the force is directly proportional to extension, or the extension is directly proportional to the force, right? So do you recall any of the laws here that you have learned in IGCSE physics? Yes, exactly. That's Hooke's law. So do you remember Hooke's law? So Hooke's law states that Hooke's law states that extension is directly proportional to force, or force is directly proportional to extension beneath the limit of proportionality. So Hooke's law is only being defined until maximum to limit of proportionality. So let us answer the question. First one, A, calculate the spring constant K of the spring. So if you remember Hooke's law, from Hooke's law, F equals Kx. If you remember, then K is called spring constant, which is equal to F over X. Since this is a straight line graph, starts from origin, whether you find the gradient of the graph or you just find the ratio of force to extension, you will end up getting the same answer because force is directly proportional to extension. So because we start our graph with origin, so you can use one of the coordinates. If you want to find the gradient, then you can use one of the coordinate as your origin as one of your coordinate. So I'm going to look for I always look for the easiest point. So I look at where the straight line crosses, okay, and I get my coordinate easily. So if you are finding the gradient, one of the important tip here that I want to give you is that make sure that the distance between the two coordinates must be large enough in order for you to get more accurate answer. So that's the tip. Remember to save it. Right. Now, the extension is 0.1 and the force is 5,000. So I'm just going to use the 5,000 force, 5,000 Newton over extension. This is 0.1 meter. So I end up getting K is equal to 50,000 Newton per meter. 50,000 Newton per meter. That's the answer. So to get the full mark, 2 marks for this, you have to sub in the correct value. You have to use in the correct equations, and you got to get the correct unit answer together with the correct units. Then only you are eligible for these 2 marks. B, a student states that the spring has not reached the limit of proportionality when a force of 4,500 Newton is applied to it. State how the graph shows that this statement is true. So when you look at the graph, where is our 4,000? Let us depend on the graph. Where is our 4,500 Newton? This is it. 1, 2, 3, 4, 5. This is the 4,500 Newton. Could you see that when the force is 4,500 Newton, the graph is still a straight line graph, indicating that the limit of proportionality has yet to be exceeded. So Hooke's law is still applicable. for force of 4,500. So when we are asked to use the graph, right, to show from the graph that this statement is true, so we could say that graph is a straight line. Okay, indicating that the ratio, okay, of force. I can use F to extension is constant. So you could also say that K is constant. Because for every spring, there is only one spring constant. That is why it's being called spring constant. Right. I hope you get the correct answer. Now, see, springs can be compressed by forces. You know, compression and stretching force, they are acting in two different directions. Stretching, you pull out, compress, you push in. You see that? You look at my hands, right? Push, pull, right? So these are directions. So directions you have to indicate by the symbol of positive and negative. Right, the spring described in Fig 1.1 is compressed by force F and has an extension of negative 0.025 meter. Determine F. Now, I prefer to use the graph, right? So where is my negative 0.025? Let me see. This is negative 0.02, negative 0.022, negative 0.024, and here it is, negative 0. I will write it down for you, don't worry. This is negative 0.025, so I have to read the force here. What is the force here? What is the value of this force over here? Now, okay, better highlight this first. Now, this is negative 1,000. This is negative 1,100 because every scale is 100. Negative 1,200. Negative 1,250 Newton. That's the answer. So I'm going to write it down. Negative 1,250 Newton. D. State whether force is a scalar quantity or a vector quantity. Explain your answer. So you could see that my force, I indicated my force as negative, and you could see from the graph, if you're blank, you don't know whether this is a scalar or this is a vector quantity, you look at the negative and positive signs. So some of the forces are positive and some of the forces are negative. So that indicates that force is a vector quantity. So force is a vector quantity. So if you are asked to explain why you say that force is a vector quantity, you can use the definition of vector quantity to explain, right? Because force has both magnitude and direction. That's the answer. Magnitude is the value, direction is the symbol of positive and negative sign. Now let us move on to question number 2. Trolley A and trolley B are on a horizontal, frictionless bench. Trolley A moves to the right with a constant velocity. U is equal to 0.44 meter per second. I better write it down. This is U equal to 0.44 meter per second. And trolley B is stationary, meaning to say that U is equal to 0. Fig 2.1 shows trolley A before it collides with trolley B. Right, okay. A, state the momentum of trolley B before the collision. Explain your answer. Now, before I give you the answer, right, do you recall momentum? First of all, to answer this question, you have to recall the concept of momentum. I want you to think of momentum as easy as a moving mass. Ask yourself, this trolley has mass? Yes. This trolley is moving? No. Right? If the trolley is not moving, if the trolley has mass and not moving, the trolley has no momentum. Because momentum, I write this down for you, momentum is equal to the product of mass and velocity. So what makes momentum so complicated? It is because momentum is a vector quantity. The vector makes momentum complicated, right? So now let us answer the question. Momentum of trolley B before the collision. Look at trolley B. Trolley B is stationary, not moving. I already wrote down there that U of trolley B is equal to 0. By the way, U represents initial velocity of trolley B. So the statement is momentum of trolley B is equal to 0. Why? Because trolley B is not moving. Initial velocity is equal to 0 and momentum depends on velocity and mass of trolley B. So for the explanation part is you can explain it using your own logic way. You can say that because momentum depends on both mass and velocity, since the velocity of trolley B is equal to 0, that is why the momentum of trolley B is equal to 0, right? Now B, after the collision, the two trolleys are joined together. Joined together, when you see this word joined together, that means this is inelastic collision. So they move together with the same speed, right? Inelastic collision. Right, and travel with a constant velocity. That is the final velocity of both trolleys moving together, right? At 0.18 meter per second towards the right. Mass of trolley A is 0.275 kilogram. Now, I would draw this. Yeah, this is before. I use different color when I draw this. This is before the collision. So I'm sorry, I hope you can forgive me. I'm not good in drawing. After the collision, you could see that I try to draw them nicely. Okay, it seems like they shrink, right? Okay, okay. Okay, this is A and B. Move together to the right with the velocity of 0.18 meter per second. I put that as final velocity. Right, okay, this is what happening. Yeah, calculate the mass of trolley B. In order to calculate the mass of the trolley B, I would like to use the principle of conservation of momentum. So do you still remember? Principle of conservation of momentum states that the total momentum before the collision must always be equal to the total momentum after the collision. So I'm going to write that down. Total momentum before collision. So you look at before the collision equals total momentum after collision. So before the collision, look at the diagram. Look at the two trolleys that the question drew, right? So only trolley A that is moving, but I still write it down for you. This is momentum of trolley A plus momentum of trolley B equals momentum of trolleys A and B. See that? Because A and B are moving together. So MAUA. MAUA represents the initial momentum of trolley A plus MBUB. U represents initial velocity. Initial momentum of trolley B, right, is equal to total momentum mass A plus mass B. If you see that this is inelastic collision, you add up the two masses because after all, these two trolleys join together. So give rise to higher mass or larger mass. So they join together, become a bigger piece of mass, right? MA plus MB times their velocity to the right, their final velocity. So MA, mass of A is given as 0.75. Initial velocity of A, look at what I wrote here, 0.44. So you just sub in 0.44 plus mass of B. I don't know mass of B, but I know initial velocity of B is equal to 0 because B is stationary. So equal to mass of A. Oh, I better sub in the value because I have the value of mass of A. So I'm going to sub in the value. Mass of A is 0.75 plus mass of B, I don't know, times the final velocity B of the two trolleys, 0.18. So from here, 0.75 times 0.44, I got 0.33 is equal to, if you want things to be easier, okay, I will teach you the fastest way to get this. Actually, you don't have to times in the 0.18 to, okay, times 0.18 with 0.75 times 0.18 with MB, no need, okay? All you need to do, okay, just to put here, okay, 0.33, straight away divide 0.18. I is equal to 0.75 plus MB, easier that way. So I'm going to do it 0.33 divide 0.18. I got 1.83. So I put 1.83. Three significant figures is equal to 0.75 plus MB. So I could see that my MB, I just put on the left-hand side, 1.83 minus 0.75, and I end up getting 1.08, 1.08 kilogram. So you could put it as 1.08 kilogram, that is three significant figures, right? That is allowed in your final answer. And you could also round it off to two significant figures, which is 1.1. So in this case, for part B, mass of the trolley, I can accept 1.08 kilogram as the final answer or 1.1 kilogram as the final answer. You will still get full marks. Now, when you see it is about the calculation question, right? And 3 marks is given here, bear in mind when 3 marks is being given, 1 mark will be given to the equation that you state. And the other mark will be given, the second mark will be given to the calculation. You sub in the correct values. And the third mark will be given to the final answer, correct significant figures, plus the correct unit. That will give you the final mark, which is A1. Now, part C, part 1, C part 1, the trolleys move into a rough surface, which exerts a constant force, F, on the trolleys and bring them to rest in 2.6 seconds. Calculate F. Right, there are a few things that I need to clarify here is that the trolley are already moving. They are already joined together. They have joined together. So I'm going to draw it out here. So these are the two trolley. I'm not good in drawing. I hope you can forgive me. This is trolley A. This is trolley B. And they are moving with 0.18. Remember, meter per second. And okay, this is a very rough surface, right? Not river, not water, just rough surface. And bring the trolley, okay? Okay, bring the trolley. So this is before. This is after, not final, after. So A and B, V is equal to 0 because, right, on the rough surface, bring them to rest. See that? And time occur is 2.6 seconds. Calculate F. Now, if you want to calculate F and if you want to use Newton's second law, yes, you are welcome to use Newton's second law. Newton's second law states that N to L means Newton's, Sir Isaac Newton's. Newton's second law states that resultant force is equal to the rate of change of momentum. Momentum, the change in momentum per time taken. Right. So the momentum before, this is the momentum before, right? The 0.18 is the momentum before of the true trolley. But you have to bear in mind at the same time, mass must be the mass, the total mass of the two trolleys, right? So I'm going to use this to solve it, right? You can also use F equals to ma. No worries with that, but just A is equal to V minus U over T. So it is actually the same thing that we are using. But it's just that when I write this down, based on Newton's second law, rate of change of momentum is equal to force. I will save a little bit of writing, right? So F mass, okay, the two masses, 0.75 plus 1.08. Okay, so I'm just going to put mass A plus mass B if you, okay? And then I put it V for you, minus mass A plus mass B times U divided by time. Easier that way. So F mass A is equal to 0.75, mass B is equal to 1.08, and V is equal to 0. Why? Because finally the two trolleys are being brought to rest. Minus MA, mass of A 0.75 plus mass of B 1.08 times the initial velocity, which is 0.18 divided by 2.6. So if you do it carefully, you will end up getting negative 0.13 Newton. Right? So final answer, whether you put in the negative sign or not putting the negative sign, it would not affect your mark because the force, the constant force that brings the trolley to rest is called resistive force. Right? So I will put in negative, just don't want you to confuse, 0.13 Newton. Right? Now, the second part, a different rough surface exerts a smaller resistive force on the trolleys. State how this affects the time taken to bring the trolleys to rest. Explain your answer. So I am going to use the equation that I stated right here. F is equal to mv minus mu over t. So could you see that the statement did not talk about the change in momentum? That also means that the momentum, the change in momentum, right, is the same. Change in momentum. That means the two trolleys are initially moving with 0.18 meter per second and finally come to rest. Okay, so I will use these to explain. Could you see that, okay, when the force is smaller, the time taken will be longer, right? So I would say that the statement affect the time, right? It takes longer time. Takes longer time to stop trolley from, okay, or to bring the trolley to rest easier. Okay, to bring trolley, I'm so sorry, trolleys to rest, right? I want to see time longer, right? Explanation is because change in momentum of two trolleys is constant. So that is why smaller force results in longer time. You could also use the equation to explain, but you have to explain every symbol that you use, where F, okay, is equal to force, resistive force, mv minus mu here represents change in momentum, and t is the time taken. No worries. If you find it hard to use to write a sentence, and if you want to save your time, I would strongly suggest you to write down the equation, but not just writing down the equation, because you have to explain every single symbols that you use. Now, the third question, Fig 3.1 shows a main electric heater used to heat a small room. A, state the region of the electromagnetic spectrum that radiates thermal energy from the heater. So it is called infrared. Infrared. Anything, any object that has heat can emit infrared. That's for your knowledge. Now, explain why the shiny metal surface behind the heating elements increases the thermal energy radiated into the room. Hey, if you have a problem in answering this question, I would strongly suggest you to look at the question number 3 itself. This is a heater. Heater is used to heat a small room. So why I have to put the shiny metal surface, right? Because I want the heat emitted by the heater, right, is not being absorbed by the metal surface back to the heater. So I want it to radiate to the room instead of being absorbed. So that is why we use shiny metal surface, because shiny surfaces are a very good reflector of heat. Right? So I'm going to write that down. Shiny metal surface, okay, is a good reflector of heat. When you write down the good reflector of heat, you gain that 1 mark. So I'm going to write down point by point. So shiny metal surface prevents heat being absorbed, okay, back to heater. So that is why it is supposed, okay, and to make sure, and making sure heat from heater is radiated into room. So you want to reflect the heat. So you don't want the heat come close to the heater. That's all. Now see, the metal outer casing of the heater is earth. So do you know what is earth? Earth means that we want the excess electrons, because you learn about charges. Electricity is about charges. There are only two charges. One is positive charge, the other one is negative charge. And bear in mind one more thing. The current is flowing due to the flow of the electrons. And the flow of the electrons must flow from the negative terminal to the positive terminal. So it is the flow of the electrons through a complete circuit that give you electricity or the current. You know, when sometimes, right, the metal casing, right? So the wire inside the metal casing got loose, they would touch the metal, and metal is a good conductor of electricity. So what if a consumer or you as a person touching the metal casing? So you will get electric shock. We don't want that to occur. So we want all the excess electrons to flow to the earth. That is one of the safety precautions, right? So I would say, yeah, to avoid electric shock, okay, when the wires inside metal casing are loose, right? Are loose, and all excess electrons, okay, can be transferred to earth, right, to be neutralized. This earth wire, right, the wire itself has a low resistance. So most of the electrons, right, electricity is just like us, you know. So electrons wants to use the easiest way to flow to the earth. Electrons will choose the easier path. Like us, I would use shortcut if whenever I can. You see that, right? So that's the reason. Now, D, the mains voltage is 230 volt. The two identical heating elements are connected in parallel. Each heating element has a resistance of 89 ohm. You see, when I see this long sentence, I would prefer to draw, right? So that I can see it clearer and I don't make careless mistake by drawing, right? So I would draw, I just draw heating element as resistor. Okay, symbol is just like resistor. Like this. So each of it is 89 ohm. Wow, that's a lot, a high resistance. And they are being connected to main voltage supply, which is 230 volt, like that. Right. And I want you to be extra, very careful here. Calculate the current in one heating element only. So if you are asked to calculate the current in one heating element, you can actually use Ohm's law. So Ohm's law, because these two heating elements are being connected in parallel to the mains voltage of 230 volt. So parallel circuit, you have to understand. Let me write it down for you. Parallel means that total voltage is the same as, okay, voltage across one heating element, voltage across the second heating element. The voltage will be the same, right? The ones that is different is the current, because this is the junction where the current splits, right? Since they asked about one current in one heating element, use Ohm's law. Ohm's law. So you remember Ohm's law? V equals IR. Right, V is the voltage, 230. I is the current, I don't know, I need to calculate. And the resistance is 89. I is equal to 230 divided by 89. So you end up getting 2.58 ampere. So if you put 2.6 ampere, two significant figures, yes, that can be accepted. So, or you can put it as three significant figures together with the answer. Together with the unit, sorry. Right. Now, the second part, show that the electrical power of the heater is approximately 1,200 watt. State any equation used in words or in symbol. So there are different equations for the power. I am going to show you, right? Different equation or different formula will result in the same answer. How about that, right? So the one that is popular, yeah, the ones that is popular one is being used, because you see, you have to read this question carefully. This is a very tricky question. They ask you about electrical power in the heater. So heater consists of two heating elements, right? So if you want to find the electrical power in the heater, you can either use P equal to IV, P equals to I square R, or P equal to V square over R. These three equations will result with the same answer. But if I want to use the V square over R, you have to find this R will be the total resistance, right? Because heater consists of two heating elements which are being connected in parallel. So you have to simplify the circuit. So if I simplify the circuit, I will do P equal to V square over R total first. Simplify the circuit will look like this, 230, and then with this R total. So since these two resistors are being connected in parallel, how do you find the R total? 1 over R total is equal to 1 over 89 plus 1 over 89. So, okay, 1 over R total is equal to 2 over 89. R total is equal to, don't put your answer in fraction, because in physics, we want to see how many significant figures you denote for your final answer. Remember that. So I'll put it in terms of three significant figures, 44.5 ohm. And now since I get the total resistance, I can use P equal to V square, right, over R. P power is equal to V square, 230 you square divided by 44.5. So you end up getting 1189 watt. You can round it off to 1,200 watt. What if you use I square R? So if you use I square R, right, I will also do it simple. Yeah, so I'm going to use V total is equal to I total, right, times R total. Since I already find the R total here, why not I just use it? Or else, okay, you have to think it using this one. 1I is 2.5, 2.59. 2.58 ampere. So this current split into two equal current because the two resistances are the same, right? Two resistances of the heating elements are the same. So this is 2.58 as well. So when you combine, the total current is the current that is coming out from the mains voltage before the current is being split equally to 289 ohm, right, heating elements, right? You can just add it out. So I total, since I draw that, so I'm going to use that. I total would be 2.58 plus 2.58, which gives you 5.16 ampere. So I'm going to use that P equal to 5.16 square times the total resistance, which is 44.5. Square times 44.5, and I get 1185. It will be slightly different due to our significant figures, right? So you could also round it off to 1200 watt. And okay, if you use IV, no problem, no problem. So power is equal to the total I and the total V. The total I will be 5.16, total V will be 230. So 5.16 times 230, you end up getting the same answer as well. But I get 1187 watt, which I'm still going to round it off to 1200 watt. So do you see that? Right? Some of the students confused. They don't know what equation that I'm supposed to use. Am I supposed to use P equal to IV? Am I supposed to use P equal to I square R? Am I supposed to use P equal to V square over R? It doesn't matter. Whichever equation that you use, it will result with the same answer. Right? I hope this is clarified. Now, the third one, the heater is 95% efficient at converting electrical work done to thermal energy. Calculate the thermal energy emitted by the heater in D part 2. In 60 seconds, give your answer to two significant figures. They have clarified that they only want two significant figures, so no three significant figures, right? So I would find the energy of heater first, which is equal to, if you still remember, power is defined as energy per time. That is why energy is equal to power multiplied by time. The power of the heater, which is 1200, times the time, 60 seconds. So 1200 times 60 seconds, I got 72,000 joules. That is the energy of the heater, right? So since I got that, I know that efficiency is being calculated from energy output, useful output energy per input energy times 100%. So 95% is the efficiency. I need the thermal energy emitted from the heater. That is the output energy. So it is the output energy. In this case, right, the output energy is heat. Most of the time, the heat is the wasted energy. But this is heater, we want heat, right? So the input energy is 72,000 times 100%. So the output energy is equal to 95 times 72,000 divided by 100. So I got, if I want to put it in terms of two significant figures, right? So I'll put it as 6.8 times 10 to the power of 4 joules, right? So 6.8 times 10 to the power of 4 joules is the answer. The next one, question number 4. A train has a maximum speed of 200 km per hour. It accelerates from rest. I love to put this, u equal to 0. From rest, u equal to 0. U represents initial velocity. With constant acceleration of 0.7 meter per second squared. That's A. This is V. Right? A, part 1, define acceleration. So you can define it as rate of change of velocity. Not a problem. But if you don't want to define it as rate means per time. You can use final velocity minus initial velocity per time taken. You could also get that 1 mark. Or you can define it as change in velocity per time taken. You get that 1 mark as well. Now, second part, show that the maximum speed of the train is approximately 56 meters per second. Now, I would like to use the definition of acceleration. A is equal to V minus U over T, where V is the final velocity, A is 0.7, and then start from rest. Okay, show that the maximum speed, right? Maximum speed. I don't have to use the acceleration. I'm so sorry. Okay, that is for the next question. I don't want to use this. Maximum speed. So maximum speed is already been given, but it is in kilometer per hour. So you have to change it to meter per second. This is related to conversion of unit. So 200, I want you to write it like this, easier, right? 200 kilometer per hour is equal to 200 kilometer per hour. So you solve it one by one. So 200, if you remember the prefixes, kilo is one of the prefixes which carries the value of 1 times 10 to the power of 3. But if you don't remember, it doesn't matter. You know 1 kilometer. How many meter is 1 kilometer? It is 1,000 meter. You convert kilometer to meter first. Meter. And 1 hour, convert to second. 1 hour, I have 60 minutes. 1 minute, I have 60 seconds. Ta-da! So I get 55.56 meter per second. You have to show this. This is called intermediate answer, right? The examiner would want to see this before you round it off to 56 meter per second. Do you know how do you get mark here? 1 mark is for conversion and 1 mark is for intermediate answer before you round it off. C means calculation, A means answer. Now, calculate the time taken for the train to reach its maximum speed. I can't wait to use the equation of acceleration. Don't you think so? I'm going to use A equal to V minus U over T. A is given as 0.7. V is 56 minus initial velocity 0 over time. Now, the time is equal to 56 divided 0.7. Let me do it. 56 divided 0.7 and you get exactly 80 seconds. But if you want to put it in terms of 3 significant figures, you can put 80.0 seconds. No lose, right? That's it. Now, B part 1, the train has a total mass of 440,000 kilograms. Wow, such a heavy train. Calculate the force which causes the acceleration of the train. If you have already calculated the acceleration or the acceleration is being given, I would strongly suggest you to use F ma. F equal to mama. Right. So you have to calculate this force. Mass is 440,000. A is 0.7. So the answer should be 308 kilonewton or 308 times 10 to the power of 3 Newton. Right? So you can put 308 kilonewton or you could put in standard form. It's up to you. Now the train travels into a headwind. The force of this headwind opposes the motion of a train. State and explain the effect of this force on the motion of the train. So there is resistive forces. So when there is a resistive forces, what will happen, right? On the motion, you cannot discuss about the force, right? The statement, you have to talk about the motion. Motion means what happened to the speed of the train, what happened to the acceleration of the train. You can say that the maximum speed of the train decreases, or you can say that acceleration of the train decreases. Or the maximum speed of the train decreases, not a problem as well, right? Explanation is that, okay, resultant force, okay, on train decreases due to you need to overcome your force on the train needs to overcome the resistive forces, right? So since mass of train is constant, okay, acceleration decreases. I'll tell you which equation that I use. So the resultant force is equal to ma. Resultant force is the force on the train minus resistive forces equal to ma. So I will say that the mass of the train is constant. So the whole thing here represents resultant force. Since the mass is constant, resultant force is decreasing, therefore the acceleration is also decreasing. So that's the answer. Number 5, a light-dependent resistor LDR has a low resistance in high light intensity and a high resistance in the dark, which is true. So if you want to think of your LDR, right, this is a symbol of LDR, like this. It depends on light, okay? The arrow represents the light that directed onto it. LDR is made from semiconductor, yeah, cadmium sulfide that will react to the light. So if you want to see LDR, you can go to the lamppost which install on your street, right? So the lamppost will light up during the nighttime. That is the application of LDR. So if you are sketching the graph of LDR, so this is a graph. Y-axis is the resistance. Normally, right, if you want it to be more accurate, right, normally when you sketch the graph in physics, you don't just put in physical quantity, but you also have to put in the unit. The unit of resistance is ohm, right? Because for the axis part, whenever you state any physical quantity, you have to state together with its unit, whichever appropriate, right? Intensity on the x-axis. So I know this is out of your syllabus. You haven't learned about intensity. This is just extra knowledge. Intensity, the unit of intensity is watt per meter square. So intensity represents brightness. So you know that from the statement that is given, resistance is low when the intensity is high, and the resistance is high when the intensity is low, right? So it is the inversely proportional graph. We want to see this, that's all. So you label your axis correctly, they will give you 1 mark, and then inversely proportional graph, that's another mark for you. B, Fig 5.1 shows part of the electrical circuit used to turn on a light when it is dark. First part, complete the circuit in Fig 5.1 with the symbol for a light-dependent resistor. So you just draw a light-dependent resistor here as to complete this, and then hit the light onto it. Yeah, arrow must hit on the semiconductor, right? So explain why the lamp is off in the light and the lamp is on in the dark. Use ideas about potential difference in your answer, right? So I would like to use when you look at Fig 5.1, first thing you recall is the potential divider concept, right? One of the things that is discussed in your syllabus, right? I will write this total voltage, right? So this is V output. Is that okay? Right. Potential divider concept is valid to series circuit only. So I want you to see this. That is why the current flow from positive, same amount of current that flowing through the fixed resistor must be equal to the same amount of current that flows through LDR. See that? Ignore the light bulb just yet. See that? The PD of the LDR is the same as the PD of light bulb. Right. So during daytime, so you just write, explain why the light is off in the light, okay? Right, bright. So I always write this first, bright time. Resistance of LDR is low. Dark, resistance of LDR is high. Right. So I am going to use Ohm's law here, but I am not going to compare the current because the current flows through the fixed resistor is the same amount of current that flowing through the LDR. Right. So during bright time, let me off in the light. Okay, in the light. Okay, I just follow the question in the light. Okay. In the light. This is how you're supposed to explain. Resistance of LDR. If they have already gave you the symbol of LDR, don't write the full sentence. Save your time. Just write LDR is low. So since current, okay, same current flows through, just compare between fixed resistor and LDR first. That's very important. Flows through fixed resistor And LDR, resistance of LDR is directly proportional to PD. I use PD because the question has already explained the symbol across LDR. So PD across LDR is low. And lamp is connected in parallel. Now only you see the lamp parallel to LDR. I explained actually more than 3 marks. I want you to understand. That is why I explained this much. I will highlight the keywords that you are supposed to explain for 3 marks later. So don't worry about that. Right. Since lamp is connected in parallel to the LDR, yeah, PD across the lamp is too low to switch on. Too low. So that is why lamp is off. Yeah, too low. Lamp is off. So, okay, the second part is that, okay, during the dark time, right? So in the dark, resistance of LDR is high. So PD is directly proportional to, okay, I just write down the word, right? Don't suggest you to use the equation. Okay, PD is directly proportional to resistance. You're allowed to use this symbol. Therefore, PD across LDR is high. Lamp, okay, lamp share the same PD as LDR. PD across lamp is high, right? That is why lamp is on. Now, let me highlight what are you supposed to write down, right? So I'll say, okay, in the light, resistance of the LDR is low, right? So you have to say that the PD across the LDR is low. That is why, okay, too low to switch on the lamp. Dark, resistance of the LDR is high. So the PD across the LDR is also high. And since the lamp is being connected in parallel to the LDR, that is why the PD across the lamp is high. That is why the lamp is on. So just a few things that you need to write down. That's all, right? I hope you understand from my statement. But if you do not understand, just comment below. Okay? Now, question number 6. Fig 6.1 shows an object O which is 5 cm away from the center of a thin converging lens L. The focal length L is 3 cm. Fig 6.1 is drawn to full scale. Now, another thing that I would like to stress here is that whenever you print out the passive questions, right, question like this, it should be printed out full screen, actual size. Then only you will get the exact value. Since I do it right on the screen, I might not get the exact accurate value right here, but I will guide you on how to answer this question, right? I hope you understand. Now, on A part 1, fig 6.1, label principal axis. Do you know what is principal axis? The one that I'm going to highlight here is called principal axis. Here. This is called principal axis. What is principal axis? I will explain here. Principal axis is just a horizontal line that pass through center of lens. Why the principal axis is so important? Because all our measurements are based on principal axis, right? So when you label, you are supposed to label P, principal axis. So I'm going to label here P. Done. Second part on fig 6.1, label a letter X at a focal point. What is focal point? Focal point is a point in which all the light will be refracted to when light passing through converging lens. Okay, so since they give you the focal length is the distance between the center of lens. Oh, I better write it down. Distance between center of lens and focal point. Okay, this object is 5 cm away, so the principal, okay, or the focal point is somewhere here. I just put here, yeah? Okay, and then since there are two curvature of the converging lens, so there must be two focal points here. So I just roughly, okay, this is just a guide. I hope you don't mind, right? This is focal point. This is focal point. And you have to label the focal point as X. So I'm going to label here X. Here, put here X. You can put on the left hand side or you can put here. Not a problem anywhere because converging lens has two focal points. Okay, remember that. Now on fig 6.1, draw two rays from O to locate the tip of the image produced by the lens. But I'm going to draw you three rays. How about that? Right? So do you still remember the rules of drawing ray diagram? First rule is that, okay, let me make this right first. Any ray from the tip of the object, right? Any ray, I'm going to use different color here. Any ray that is parallel to the principal axis or horizontal to the principal axis will be refracted at principal focus or the focal point. So refracted here. This is just a guideline. Yeah? I don't get the exact answer right here because I am doing it digitally. I hope you can understand. So whenever you draw, just draw refracted. Draw longer. Right? And then don't just leave it like that because ray, you have to show the arrow of the ray. Right? That is the first ray. Okay? Second ray, I'm using different color. Okay, green color maybe. The easiest one. Any ray that passes through the center of the converging lens or any of the lens from the object, okay, will just go through straight. You see that? So this one I might need to draw longer. Give me a while. Okay. Here I might need to draw a bit longer. Yeah. Okay, just a bit longer right here, right? So you just assume that this is a straight line, right? And the third ray, oh, forgot. You have to draw arrow. Okay, all you need is just these two rays, right? The third ray is extra. So the third ray, I am going to draw it out, still going to draw it out. The third ray is that any ray that pass through the focal point first, like this. Wow. Okay, like this. Wow. Okay, hard to draw, but still I'm going to draw it. Make sure that you understand. Start from the tip of the object all the way, right? This is extra, yeah? Extra. Just want you to know this is extra. Might not be very nice because my ray is so low below. So will be refracted. I'm going to delete that ray because my diagram is so out. Okay. Okay, only these two matches. So must be refracted horizontally, right? So the intersection of the three rays will give you the exact location of the image, right? Now let me delete this ray because you don't need it anyway. So this is where the image being formed. So you just imagine that this is a very nice one. So you have to measure it. Without measurement, you couldn't possibly get, right? So why I say the principal axis is a point, right? It's a horizontal line where all the measurements are based because this is where the location of the image is being formed. So you can compare. If you want to know the characteristics of the image, you see, part 4, in table 6.1, place a tick in the right-hand column next to all the terms that describe the image in A part 2. Could you see that the height of the image is definitely taller as compared to the height of the object? So we say that the image is enlarged. Could you see that? When I say that all the measurements are made from the principal axis, object from the principal axis is going upwards. Image from the principal axis, where the image is formed, below the principal axis. Object is above the principal axis. So that is why the image is called inverted. As long as the image is formed at the back of the lens, the image is called a real image. So you have to show 3 ticks here. That will do. Now, B, the object moves closer to L. The new distance between L and the object is less than the focal length. Less than the focal length. Describe how the new image is different from the image in A part 4. Okay, I will use the annotation to show you right here. When the image is being moved, okay, let's say somewhere here. Okay, this is the object. Okay, object, same height. Okay, maybe lower height. Now, see what happened here? Okay, you can draw. I will delete this later, don't worry. Any ray, oh, I just want to label that this is object, yeah? This is object. Object right here. I will erase this, but I want you to see. Any ray that is horizontal or parallel to the principal axis will be refracted at focal point. You see that? And the second ray, we cannot draw the third ray, we can only draw the second ray. Any ray that is passing through the center of the lens will just go through straight. Could you see that as well? Now I want you to see that, okay? Could you see that the distance between these two rays are getting closer? So somewhere up here, the image can be formed. So that is why all you need to do is just extrapolate. But you extrapolate when the image is formed in front of the lens, right? You have to draw dotted ray to show that the image is virtual. Image that is being formed in front of the lens is called virtual image. Could you see that? Image is being formed here. So this is the exact location of where the image is being formed. Could you see that compare object and the image is taller. And since the image is being formed in front of the lens, image is said to be virtual image, right? And this concept is being used in magnifying glass. See that? So I'm going to answer the question right now. The new image is different because the new image, okay, new image will be formed in front of lens. We call this as virtual image. And on the same plane as object. This is being called upright. It is above the principal axis. Image is also above the principal axis. That is why it is called upright. Right. Question number 7A. Fix 7.1 is the scale drawing again of light waves approaching a narrow slit. The scale 1 cm is equal to 4 times 10 to the power negative 7 meter. So this is the direction of propagation of wave. Name the wave effect produced by the narrow slit. Wave pass through narrow slit. Do you recall? This is called diffraction. What is diffraction? Diffraction is the spreading of the waves when the wave passing through a small narrow slit here. Right. So if you want to know more about diffraction, I would suggest you to watch one of my YouTube channel, which I talk about diffraction and how to draw diffracted waves. Right. I hope you gain benefits from that. So diffraction, if you want to think of the diffraction in the real life, you just imagine you go to the cinema, right? You watch a movie, and there's only one small exit in the cinema, and suddenly somebody shouted, fire! What happened? Everybody will be rushing towards that small little exit there. Everybody will be pushing everybody. So what will happen when everybody gets out from the small little exit? That is what I'm going to draw, right? So using fig 7.1, determine the wavelength of the light. So you could see that I just want you to bear in mind. Some of the students confused. Where's the wavelength, right? I don't know where's the wavelength. Wavelength is not being given. Don't worry. Distance between one wavefront to the other wavefront is called wavelength. So all you need to do is just to measure this distance. And so happen that this distance that I measured maybe is not so accurate, right? This distance that I measure, yeah, is equal to 1 cm. Wavelength is equal to distance between two successive wave fronts. Remember that, right? So if you measure differently, it doesn't matter. It doesn't matter. So I measure 4.0 times 10 to the power negative 7 meter, right? Okay, 4.0 times 10 to the power negative 7 meter. So you need to print out in full size, actual size, then only you do your measurement. That would be most accurate. Right, on fig 7.1, draw three wavefronts that have passed through the narrow slit. Right, so since you want to know whether this is a great diffraction that occurred or small diffraction that has occurred here, all you need to see is that I give you one important tips here. You compare the length, right, of the wavelength and the length of this slit. If the size of the slit is similar, right? Not much of the big differences here between the small slit, narrow slit, and the wavelength, then greatest diffraction has to occur. That means the wave, okay, will undergo, okay, a large diffraction. So how do you draw a large diffraction? Let me guide you. First of all, when diffraction, you see, when they ask you to draw diffraction, they always give you 3 marks. 3 marks, 1 mark will be given to the pattern, right? So the pattern will be, wow, everybody pushing, everybody push out from the cinema. There's a fire here. That is how you draw. And then diffraction, bear in mind, nothing changed to the wavelength. So you have to draw almost similar wavelength. The gap between the wavefronts must be similar. So I draw almost similar. I try my best, almost similar. And all you need to do is just to draw three. Okay, maybe not so nice. Here. Okay. Okay, circular wave like this. Can you see that? Make sure that this lambda is almost constant from the naked eyes, right? Pattern 1 mark, no change in the wavelength constant after diffraction, 1 mark. And the third mark, do you know how to get? You have to show arrows because diffraction, after all, means spreading of waves when the waves is passing through a small opening. So you have to show that the waves has already spread out when the wave passed through that small opening. That's it. Now B, a foghorn emits a sound with frequency 380 Hz. The sound is heard by a ship 2.5 km away from the foghorn. Speed of the sound in air is 330 meters per second. First one, show that the wavelength of sound is approximately 0.9 meter. State any equation that you use in words or in symbols. So I'm going to use V equal to F lambda. This is the equation of wave speed. This is wave speed. This is frequency. And this is the wavelength. Now, wave speed is given as 330, frequency is 380, and lambda is the wavelength. So to find the wavelength is 330 divided by 380, and I got 0.868 meter. And, okay, before you round it off, you have to show this because 1 mark will be given to that. So then only you round it off to 0.9 meter. That's it. Second part, calculate the time it takes for sound to travel to the ship from the foghorn. Distance, still remember speed is equal to distance over time. Speed of the wave is 330, distance is 2.5. Bear in mind, look at the unit of speed. The unit of speed is in meters, so that is why distance must be put in meter as well. So 2.5 kilometer, you have to convert that kilometer to meter divided by time. Time is equal to 2.5 times 1000 divided by 330. So you got 7.58 second or 7.6 second. I put it in terms of three significant figures. Now let us move to question number 8. Fig 8.1 shows a metal rod suspended in a magnetic field produced by a pair of permanent magnets. Metal rod is connected to a cell. There is a current in a metal rod. This is super duper important. You have to highlight it. So there is a current in the metal rod. That means this has nothing to do with Fleming's right-hand rule. This has nothing to do with electromagnetic induction. Right? Now, A, state the direction of the force on the metal rod due to the current. So, first of all, this is the understanding of the current. So you have to understand that the current will flow out from the positive terminal to negative terminal, back to the negative terminal. So this part is where the current is flowing. And magnetic field, invisible magnetic field will flow out from north into south pole. That is another thing that you should remember. So since there is a current flows in the metal rod, there will be magnetic field around the metal rod, right? Right, current carrying conductor has magnetic field around it. Right, the interaction between the magnetic field of the metal rod and the permanent magnet gives rise to the magnetic force. That is why you are asked to determine the magnetic force. Right? That's the origin of the magnetic force. Now, to determine the direction of the magnetic force, we use our Fleming's left-hand rule. Find my cat. Find force. Thumb represents force. First finger represents magnetic field. My cat represents direction of the current. So first of all, if you want things to be easier, you use first finger first. Right? Align with the direction of magnetic field, which is north to south. See that? And then current seems to be go into the screen. So you just push the second finger into the screen. Look at my thumb. Where my thumb is pointing, my thumb is pointing downwards. That is why the direction of the force is downwards. Downwards. Right? Explanation, how do you get the downward force? Right? I better write it nicely. Okay, this is downwards. D-O-W-N, downwards, right? Explanation is by using Fleming's left hand rule. Thumb represents direction of force. First finger represents direction of magnetic field. So you can write N pole to S pole. And second finger, this one I write extra. Finger represents, I will highlight the keywords that you're supposed to write in your answer. Represents direction of current. So if you draw anything on the figure that they provided, you can actually ask the examiner to refer to the figure. Okay, refer. Fig 8.1, no problem, no harm, right? They won't deduct your mark because of that. You know, some people, they are not good in explanation, but they draw something. So that is why the examiner will use the figure, right, to give you the mark, right? And the direction of force, magnetic field, and current must be perpendicular. Current flows from positive terminal of cell to negative terminal. So you can ask the examiner to refer to your figure. So what are you supposed to write down for the 2 marks explanation, right? So you have to talk about Fleming's left-hand rule, and you have to talk about force, the direction, force, magnetic field, and current perpendicular, and the current must flow from positive to negative. We want to see that. Okay? Now B, the connections to the cell are reversed. When the connections from the cell reverse, right? That means, I'll show you right here, that means the current will flow from downwards, out from the screen. So what can you see is that you're still using the Fleming's left-hand rule, north to south, but the current now is out, pointing the second finger at yourself, and look at my thumb is pointing upwards. Is that okay? So how this change affects the force on the metal rod, okay? Direction of the force is reversed. Or you can say, okay, direction of force is reversed. But the force, the magnitude of the force is still the same. Yeah? Okay, same magnitude. It's just that direction changes. Yeah, you can also say outwards. No problem, outwards. Now, see, two magnets and a cell are used to make a simple electric motor as shown in Fig 8.2. Describe the function of parts J, K, L, and M. So I'll do it part by part. You look at J. J is called carbon brush, right? I'll write down the name, carbon brush. What is the function of the carbon brush? To brush thing? No. Carbon brush, you see where if you confuse, right? I want you to see. Carbon brush is being connected to M and what? And cell. Cell is the one that provides the current to the whole circuit. So carbon brush will act as a completer so that the current can flow from the cell to the coil. Remember? Yeah. So to connect cell and coil, yeah, so that the current can flow through the coil as a circuit completer. Okay, K, look at K. K is what? K is a coil, right? Coil that made of copper, right? So why? Because the copper has a low resistance, right? High conductivity. So what is the function of the coil, right? To allow current to flow through it, right? And then it can, when the current flowing through it, it has its own magnetic field that will interact with the magnetic field of the permanent magnet, which gives rise to magnetic force. Okay, and then L, what is L? L is the axis of rotation. We call it as axle, right? What is the function of the axle? It is to support rotating coil. Normally, the axle is installed at the center of the coil, right? So the last one, which is the most important one, which is M. M, I want you to think about this. When you look at electric motor must be supplied with the current, okay? Because it converts electrical energy to mechanical energy, maybe kinetic energy, right? Like your escalator, we use electric motor. So this M is called ring, a perfect ring that is being split to half. It is called split ring. Commutator. So what is the function of the split ring commutator, which used to be super duper important in most of the past year physics paper form, right? So it is to make sure coil turns in one direction. Direction only. How? I give you extra by reversing the direction of current on two sides of coil every half a cycle, right? So you could see that here. There are two different currents flow, yeah, in two sides of the coil. So commutator, right, when the coil has already turned, it will reverse the direction of the current every half a cycle, right? That's it. Now, question number 9. Strontium-90 is a radioactive isotope of strontium. Nuclide notation for strontium-90 is 9038SR. A part 1. Explain what isotopes are. Isotopes means that, okay, nuclides with the same number of protons but different number of neutrons. If you don't like to put different number of neutrons, you could put nucleons. Different nucleon number is not a problem. And I want you to bear in mind is that isotopes, right? For neutral isotopes, they exhibit the same chemical properties because chemical properties are being determined by the number of electrons. Since they have the same number of protons and they are neutral, they must have the same number of electrons. So that is why they will give you the same result when you conduct chemistry experiment on them. Right? So, but doesn't mean that they have the same physical property. Physical property is that, okay, some of the isotopes are solid, some of the isotopes are liquid. That is what we call physical properties. Complete table 9.1 for strontium-90. So number in one atom, okay, 38. Location is outside the nucleus. You bear in mind, it cannot be proton because proton is inside the nucleus. Inside the nucleus consists of proton and neutron. The one that is outside the nucleus is called electron. Don't make this careless mistake. Remember that, yeah? This is electron. And then neutron. How to get neutron? Neutron, it is nucleon number minus proton number. So it is 90 minus 38. You get 52. That is your neutron number. So neutron is inside the nucleus. And 38 as well. What is inside the nucleus? It is definitely proton. Right? That's the answer. Now, B, strontium-90 is used to measure the thickness of metal sheets in industry. Right? Strontium-90 decays by emitting beta particles which pass through a metal sheet to detector. On metal sheet, one metal sheet is 0.75 millimeter thick, suggests why strontium-90 is a suitable radioactive source to measure the thickness of the metal sheets, which is also true. Let me tell you about the beta decays, right? The nuclide that emits beta particles. So beta particles are being used to control the thickness of the sheet, thickness of the paper that you printed out. They are of the same thickness, right? So thanks to these beta particles, right? Why strontium-90 is suitable? Because strontium-90, right? Because of this beta. So do you should remember the beta particles? They are fast-moving electrons. They can be stopped by a few mm of aluminium sheet, right? So since this is a metal sheet and it is still within so it is suitable because beta, you can use the symbol. Beta can pass through metal sheets, right? And can be stopped when thickness is increased to 0.575 mm thick. So hence, thickness of metal sheet can be maintained or can be controlled. So what would happen, right? If the thickness is different, so the reading, right, that on the detector will be different. So indicated that the thickness of this metal sheet has already been altered. So you need to make some adjustment to the, right, to the thickness. So the second part, the half-life of the strontium-90 is approximately 27 years. Do you still remember what is half-life? Half-life is time taken for the strontium-90 to decay to half of its original number or original activity or original number. It's up to you, right? Or original count rate. Approximately 27 years. Fixed 9.1 shows the shape of the decaying curve. This is exponential decay. Strontium-90 source is replaced with a new source after 15 years. You see, 15 years is here, right? I will highlight this. 15 years drop. Okay, this is 15 years. This is half-life, 27 years. You see that? I want you to see this. Okay, this is 15 years. This is about, okay, 27, somewhere here. Okay, now using Fig 9.1 suggests why strontium-90 source that is more than 15 years old needs to be replaced with a new source. Could you see that initially is 100%, but when it is more than 15 years, right, it drops a lot, right? It drops lesser to 50% of percentage of the strontium-90 remaining is 50%. So what harm that has to be? Yeah, has to be done. Why you have to replace? It is because, right, the remaining strontium-90 is very less. So since the remaining strontium-90 is very less, so it would emit weaker radiation of beta particles. So weaker radiation, that also means that the thickness of the paper, right, could not be controlled effectively. So that is why we have to replace it. So I'm going to write it down. Nuclear number of strontium 90 remaining is very less, I said. So weaker beta particles radiation from strontium 90, right? So no, 90 degrees, I'm so sorry. Not strontium 90. So thickness of metal sheet cannot be controlled effectively. That's the answer. Now, question number 10. Fig 10.1 shows the path of the Earth as it orbits the Sun. X is a position on the Earth where the scientists observe the apparent motion of the Sun throughout the year. A. Determine how many days it takes the Earth to move around its orbit from F to G. Explain your answer. You see, from F to C, F to G, G to H to E, and back to F. That is, okay, when the Earth finish one orbit, right? The time taken, right? The period of rotation, right? The period of the orbit of the Earth is 365 days. F to G, you split it out. So there are four positions of the Earth here. F to G is 1/4, right? So number of days is 1/4 of 365 days, right? Which is, I'm not going to write the answer, okay? So the answer is 91.3 days. Explanation is because when, okay, Earth orbits from F to G, okay, it takes 1/4, right, of full orbit, which is 365 days. That is why you get 91.3 days. Now, B, fixed 10.1 shows four positions, E, F, G, and H of the Earth in its orbit of the Sun. First part, identify the position of the Earth when it is summer at X. If you want to see it easily, right, you look at the location of X. X is more, to me, when you look at it, more on the northern hemisphere. So if you want it to be summer, then due to the tilting of the Earth, right? Remember, Earth is tilted. When Earth tilted towards the sun, right? Then position X will experience summer, right? The people from the country on position, location X will experience summer. Could you see that on F, right? It seems like, okay, the Earth is tilted towards the sun and X is here. So at position F, right? The Earth is summer at X. F is the answer. Second part, identify the position of the Earth when it is winter. Winter is when the Earth tilted away, right? X is going away from the sun. So X do not get as much sunlight, as much heat from the sun. So where is it? Can you see? Position H here. X seems to be tilted away. So H is winter. You see that? Okay, now the orbital speed of the Earth around the Sun is approximately 3 times 10 to the power of 4 meters per second. Calculate the average radius of the Earth's orbit. Okay, do you still remember the orbital speed is equal to 2 pi r over t? Right, the speed is 3 times 10 to the power of 4. This is 2 pi r. R represents the orbital radius of the Earth's orbit. And time taken for the Earth around the Sun is 365 days. One day, you have 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. Make R as the subject. R is equal to 3 times 10 to the power of 4 times 365 days times 24 times 60 times 60 divided by 2 pi. Right? So when you do it nicely, R that you are supposed to get is 1.51. I put in 3 significant figures times 10 to the power of 11 meter. You could put 1.5 times 10 to the power of 11 meter. Okay, now last part. Earth is a planet in the solar system. State one other type of naturally occurring object that is present in the solar system. So you can state many stuff actually present, right? So it could be asteroids, it could be meteoroid, it could be just state one, comets, etc. Right? So, and that's it. We have completed the full walkthrough of IGCSE Physics, February, March 2025, paper 42. I hope this gave you a clearer idea on how to approach each question, yeah? And how to write your answer, right? In order for you to gain that full marks and what to expect in your upcoming exams. So if you want a full PDF of my annotated answer and tips for this past paper, please subscribe to my YouTube channel, TikTok channel, and my Instagram, and just snap picture, right, of the proof that you have already subscribed, and just send Instagram message to me, and I will send this PDF, annotated PDF, to you right away. And thanks for watching. I'll be seeing you in my next video, and keep learning. And remember one thing, physics is not about memorizing. Physics is about understanding. Bye.